Hello, welcome to my space station. Today we'll be talking about antimatter. So, I think you all would have heard about the term antimatter before. So, today I'll be clearing the doubts on antimatter. So, let's get started. Antimatter is basically the same as ordinary matter, but it has a completely opposite charge. For example, a proton might have a positive charge, while an antiproton would have a negative charge. An antiproton would have the same qualities as the proton, the same mass, the same characteristics, but just a different charge, the opposite charge. So, antimatter is basically something that is produced mostly in space, but it can also be produced on Earth. The place where it is produced the most is the Large Hadron Collider. Now, the special quality of antimatter is that it annihilates itself and matter if it comes into contact with any type of matter. So, if an antiproton comes into contact with even an anti-hydrogen atom, it will still eliminate each other. They will still eliminate each other even though they might not match. So that is the thing why antimatter cannot be stored for a long time. It just eliminates itself and matter. So usually the antimatter is stored for a very short time, and the world record for the longest time antimatter was stored was in the CERN laboratory for 1,000 minutes. Anti-hydrogen atoms were stored there. So how antimatter is usually stored for long periods of time is through magnetic fields. Since you can't store it in a container or something, it would just eliminate itself. You suspend it in an area where there are strong electromagnetic fields, and so they make it so that the atom cannot move too much. So it remains trapped in a specific place for a while until it finally frees itself from the power of the electromagnetic field and eliminates itself. So one of the other difficulties in keeping antimatter is its production. So I'll give you two pieces of information. The Large Hadron Collider would need 9 times 10 to the power of 20 joules of energy to produce 1 kilogram of antimatter, and it would take more time than the current age of the universe to produce 1 kilogram of antimatter. Yeah, you understood that, right? It will take a lot of time and a lot of energy to create sufficient antimatter for the purpose that people usually intend it for. Antimatter has many uses. One of the more biggest uses is the use in quantum mechanics. So it is used to describe how small particles behave in very tight spaces. And it's also used a lot in medicine. There's a thing called PET, which antiprotons are used to treat people, and it's also used to detect the metabolic activities of the body. And antimatter is also theorized to be used for powering rockets. As when antimatter eliminates ordinary matter, it releases a lot of energy. If we have 2.4 kilograms of antimatter, it will have the same power as the power of the Tsar bomb. The Tsar bomb is the biggest and the most powerful nuclear bomb in existence, and just 2.4 kilograms of antimatter would have enough power to match that of the Tsar bomb. So it produces a lot of energy, and that's why it's also very dangerous. It has to be stored in perfect conditions, and that's why people have theorized that if we take some antimatter and we keep it safe under magnetic fields, and when the time is right, we expose it to matter, and so it will get lots of energy, and so that would potentially power a rocket. Assuming that the antimatter doesn't just destroy the rocket, it should theoretically power the rocket with lots of energy, something our current thrust boosters cannot achieve. So that is basically what antimatter is, and the use of antimatter was predicted by Paul Dirac. So he made an equation which calculated the energy of normal atoms, and it was there that if you put some energies in, it would give you an answer in negative. And so when people said that okay, this is not working, then Paul Dirac said that okay, it's possible that there is some other force, some other type of atom which had negative energy. And soon a different physicist proved this idea by using what's called a cloud chamber, where you have atoms, and those atoms' existence is proved by different clouds of magnetic fields. And so what he observed is that if he took the correct energies that were in the equation, he saw that a few atoms were flowing opposite to the magnetic field. So while most of the atoms, let's say, were flowing right, few atoms were flowing left. And he said that okay, this is proof that there's some different particle which exists. And later on, through the Large Hadron Collider, it was physically proven that yes, antimatter can definitely exist, and it certainly does. People the Large Hadron Collider does produce small, tiny quantities of antimatter. Usually, the process that is used is that the atom is sped up a lot, and it is like very like it's sped up a lot. That means like it has to be contained in a way that even if it escapes, it could cause lots of destruction. So it has to be contained, has to sped up a lot, and has to be smashed against an iridium wall. Now the bigger details of this are very complicated, so I won't be sharing them in this video. But generally, it's hit against a wall made of iridium, and that causes the matter to split into different antimatter. And then the antimatter has to be stored perfectly for a period of time they want to do whatever experiments they want to do. This is a very delicate process. It takes lots of energy to speed the atom up to the desired speed. So that's why the Large Hadron Collider doesn't produce much quantities. Like I told before, it takes lots of energy and lots of time. So one more quantity or quality of antimatter would be that it violates CP. Now CP is short for conjugation and parity. Basically, it means that if you take a particle and you create its antimatter opposite and you mirror the particle, the laws of physics should be the same in that particle. Usually, things should abide by the CP theory, but things that don't, they violate, they do a CP violation, and it's a quality that is observed mostly in kaons. Kaons, a type of particle which is made up of different quarks which we haven't actually identified yet. It's a strange particle. What happens is that its decay time is different. Let's take an example. It decays for once in 10 milliseconds and the next 14 milliseconds. There's a different decay time. Usually it's not supposed to be like that, but with kaons that is the case. And so this is one of the examples of CP violation. Basically, when you take an antimatter and mirror it, the laws of physics should remain like normal. So antimatter have been found on more than one occasion to violate CP. Usually when you make antimatter into a matter and mirror it, you sometimes don't follow the laws of physics. And the details, if you want to know, I'll make a separate video on it because this is a very complicated topic. This also is one of the biggest unsolved mysteries in physics. Why, when the universe was produced, there wasn't the same amount of matter as antimatter? There's actually more matter in this universe than there's antimatter. And normal people, like doing calculations, it would give you the answer that matter and antimatter should be equal, but that's not the case. People have tried to use CP violation to try to explain this, that okay, why isn't there enough antimatter? It's a bit like the NP versus P problem in computer science. People say that it's impossible to solve. Maybe it will be solved if you have the right enough time, but right now there's no proper solution that is given for this problem. Why isn't there more? Why isn't like the matter and antimatter same? So the antimatter field is like a very complicated field. There has been lots of works on it ever since Paul Dirac made his equation, but we haven't been able to make any great breakthroughs in recent times. So it still remains subject of mystery. So that was the entire video. I was trying to share you about antimatter. So I'll see you in another video. Bye bye.